I am the very model of a modern major general. I've information, vegetable, animal, and mineral. I know the kings of England, and I quote the fights historical, from Marathon to Waterloo in order categorical. I'm very well acquainted too with matters mathematical. I understand equations both the simple and quadratical. About binomial theorem, I'm teeming with a lot of news, with many cheerful facts about the square of the hypotenuse. I'm very good at integral and differential calculus. I know the scientific names of beings animalculous. In short, in matters vegetable, animal, and mineral, I am the very model of a modern major general. That's right, I couldn't go talking about quadratics without a little Pirates of Penzance reference. Hello, welcome to Class 2 of Unit 8, Quadratic Equations in Intercept Form, Part 1. Now, last time we were together, Mama Volel so graciously helped introduce us to the standard form of a quadratic equation in two variables. Now, if you don't remember, shame on you, how dare you, but I'll refresh your memory for you, I'm feeling generous. Remember, it's not too different from the standard form from Unit 7. Only difference, of course, is that it starts with a y equals, but everything else on the other side is the same. I start with my quadratic term, followed by my linear term, with my constant at the back. Just like linear equations, the idea is that quadratics can appear in a number of different forms. And when it comes to graphing, it turns out, for reasons we will soon see, that standard form isn't always the most helpful. But if nothing else, we can at least use it to do a little evaluating. Say, for example, that I want to evaluate the equation y equals negative 2x squared plus x minus 2 for each of these values of x. What exactly is it that I'm asking you to do here? And if you're feeling bold, take a minute, pause the video, go ahead and do it for me. Can you accomplish this task? Go! Okay. Well, again, remember, evaluate doesn't mean anything too crazy. It's just a fancy word for substitute. So what I'm trying to do here is take my equation, and for each of these values of x, right, every time that I see an x in my equation, I'm going to substitute in the value of x that I'm evaluating for. So here, y is going to be equal to this guy on the right. All I need to do is simplify the right-hand side, and I'll get a value for y. So here, negative 2 times 0 squared, which is just 0, plus 0 minus 2. Negative 2 times 0 is 0. And putting it all together, 0 plus 0 is 0. 0 minus 2 is negative 2. Now that's great, but in context, there's a method to the madness, a reason why I want to be able to evaluate. If y is equal to negative 2 when x is 0, what that communicates to me is that on the graph of this equation, the point 0 for x and negative 2 for y should appear. And on this graph, this point is actually something interesting for me. It's one of my characteristics. What is this guy in context? 5, 4, 3, 2, 1, 0. Emphasis on that 0, because when x equals 0, I know I've moved neither left nor right. I am on the y-axis. So this point is my y-intercept. Very nice. If you haven't already, let's do it together for x equals 3 and x equals negative 1. Again, my strategy is just to do a little substitution. So here, every time that I see x in my original equation, I'm going to replace it with positive 3. Simplifying the right-hand side, negative 2 times 3 squared means negative 2 times 9. Negative 2 times 9 is negative 18, and then I've just got to combine all my like terms. Negative 18 plus 3 is negative 15. Negative 15 minus 2 gets me to negative 17. What this, of course, tells me in context is that the point 3 comma negative 17 should show up on my parabola. And last but not least, x equals negative 1. So here, if x is negative 1, y is going to be negative 2 times negative 1 squared plus negative 1 minus 2. Simplifying, negative 2 times negative 1 squared means negative 2 times 1. Plus negative 1 really just means minus 1, and then minus 2 at the back. Negative 2 times 1 is negative 2. And then combining all those like terms, negative 2 minus 1 is negative 3. Minus 2 from negative 3 gets you to negative 5. So again, in context, that means that the point negative 1 comma negative 5 should show up on my graph. Cool. So we can use standard form to find points on our graph. And if we think back to Unit 4, finding points was pretty much the whole point of graphing. So if I've indicated that standard form isn't the best form for graphing, what exactly about standard form is it that makes graphing hard? Or harder than it needs to be, at least. And the thing that I want you to think about is that when we're graphing a parabola, it's going to be necessarily different from graphing a line. Take 30 seconds, pause the video, take a risk, take a chance. What do you think makes graphing parabolas different from graphing lines? Go. Okay. Well, hopefully you've got an idea percolating around in that brain of yours. Hopefully there's something in your brain at the very least, and it's not AI slop. So, if I want to build the graph, I don't know any fancy techniques yet. Let's try that plug and chug strategy that we did last time when we were building the graph of our parent. So I'm going to give myself some values of x and some values of y. I'm going to see why the process of graphing might look a little bit different. So here, easiest place for me to start. Well, if I plug in 0 for x, I can find my y-intercept. Not only that, but it's a nice friendly number to work with here. So y is going to be 0 squared minus 2 times 0 minus 3, same strategy as above. Well, 0 squared is 0. Negative 2 times 0 is also 0. And then I've got minus 3. 0 minus 0 minus 3, put them all together. We get negative 3. What this, of course, tells me in context, right, I want to find points. So the point 0, negative 3 is going to be on the graph of my parabola. That guy lives right over there. Cool. Remember from last time, I want to find at least 5 points on the graph of my parabola, so let me find 4 more. If I've used 0, the next nicest number would probably be positive 1. So let's try. Y is going to be equal to 1 squared minus 2 times 1 minus 3. 1 squared is 1. Negative 2 times 1 is negative 2, and then minus 3 at the back. 1 minus 2 is negative 1. Negative 1 minus 3 is negative 4. So this tells me, again in context, the point 1, negative 4 should appear on my graph. That is right there. 3 more. If I've done positive 1, let's do negative 1. So negative 1 here, that would be y is equal to negative 1 squared minus 2 times negative 1 minus 3. Negative 1 squared means negative 1 times negative 1, which is positive 1. Negative 2 times negative 1 is positive 2, and then my minus 3 at the back. 1 plus 2 is 3. 3 minus 3 is 0. So would you look at that? We found an x-intercept at the point negative 1, 0. Cool. Let's go over to the right now. I've done 1 and negative 1. Let's try positive 2. So here, with positive 2, y is going to be equal to 2 squared minus 2 times 2 minus 3. 2 squared is 4. Negative 2 times 2 is negative 4, and then minus 3 at the back. 4 minus 4 is 0. 0 minus 3 is negative 3. So the point 2, negative 3 should show up on my graph. When I was graphing lines, it would be weird that that y value of negative 3 showed up twice, but remember our parabola is symmetrical. It makes sense that we're going to have 2 points with the same y value. So in fact, knowing that I'm symmetrical, let me keep going to the right. That should give me my other x-intercept. Logically, I would expect that to happen when x is 3. So here, y is going to be equal to 3 squared minus 2 times 3 minus 3. Simplifying, 3 squared is 9. Negative 2 times 3 is negative 6, and then my minus 3 at the back. 9 minus 6 is 3. 3 minus 3 is 0. Look at that. 3, 0 is going to be our second y-intercept of our graph. Last thing I need to do to complete my picture, well, let me just draw in that parabola, and we're going to pretend that it's beautiful and perfect, and you are not going to say anything about it. Ooh, that's wonky. Let's try it again. Cool. So let's say this is our parabola. It's not perfect, but who cares? None of us are. Now, graphing this wasn't too bad, but there's a reason why it wasn't, and it's in fact the answer to that question that I asked you to think about with how graphing parabolas is different. Here, we happened, by chance, to stumble upon the most important part of our parabola, which is, dun dun dun, its vertex. But just because we found the vertex here by chance doesn't mean that we will always be so lucky. So in other words, the answer to our question, why is standard form maybe not the best for graphing? If finding the vertex is the key to graphing the parabola, in standard form, the issue is that we're not always going to have an obvious place where our vertex should be. We won't know off the bat where that vertex lives. So what this hopefully tells us is that the plug and chug strategy we just tried has diminishing returns. When it comes to graphing our quadratics, we need to know where the vertex is, but finding it can be tough when we don't know where to look. So, if the idea is that blindly plugging into standard form and hoping we get lucky isn't very practical, to make graphing easier, we need a form for our quadratics that will help us find the vertex. And to help motivate where one such form comes from, let's see if we can notice any patterns about the relationship between each of the vertexes here in these graphs and any of their other characteristics. So take a look here, take a risk, take a chance, be creative. Do you notice anything about where each of these vertices in green lives relative to the other points on each parabola? See what you come up with, and if you don't get anything, that's okay, but I want you to try. Go! Alrighty. Well, there are lots of things that we could say here, but the thing that I was hoping you noticed. Remember, as I alluded to above, that our parabola is symmetrical. There's an axis of symmetry that always passes through our vertex. And the interesting thing about that axis of symmetry that passes through the vertex means if I look specifically at any pair of points, but maybe let's focus on the x-intercepts down here, up there, down here, right? The distance from the axis of symmetry to each of those intercepts, or in fact really to any of the points on my graph, should be the same. So the interesting thing that we'll notice, right, because our parabola is symmetrical, it will always be true that the vertex is going to be right in the middle of our x-intercepts. In other words, it's going to be halfway between those x-intercepts. And if we want to be really annoying, there's a mathematical way that we can indicate the in-between of two numbers. What's the mathematical concept that helps me find the midpoint of two values? Go, 5, 4, 3, 2, 1. Well, we've used this idea a couple of times in class before. If I want to find the midway point between two things, mathematically what I'm doing is finding the average of my two values. So if I can find the average of the x-intercepts, then I can find at least the x value here of my vertex. Cool. Let's write that down algebraically. What that means then is if the vertex of my parabola is the point h comma k, and my x-intercepts are things p comma 0 and q comma 0. Whatever p and q are, right, y always needs to be 0 if I'm on the x-axis. To find the average, I add up my two numbers and divide by 2. If it was 3 numbers, I'd add them all up and divide by 3. So what that tells me here is that the x value, h of my vertex, should be equal to the average of the x-coordinates, p and q, of my intercepts. Very nice. With this idea in mind, having just discovered this relationship, you should now be able to find not just the intercepts, but the vertex of this equation, y equals x squared minus 9. Take 2 minutes, pause the video, find me those x-intercepts, and use them to get me that vertex. Go. Alrighty. Well, to find the x-intercepts, again, let's be really explicit. If I'm on the x-axis, then y is equal to 0. So I need to take 0, plug it in for y, and use that to find my values of x. So if 0 is equal to x squared minus 9, notice here that x squared minus 9 is a difference of squares. Using my difference of squares pattern, at the front, x squared needs to be x times x. My difference of squares gives me a difference of signs, and then 9 would come from 3 times 3. From here, using my 0 property, I can now do some splittage. So either x plus 3 is 0, or x minus 3 is 0 if I multiply them to get 0. Subtracting 3 from both sides on the left reveals that x could be negative 3. Or on the right, adding 3 to both sides, x could be positive 3. So here are my intercepts, x equals negative 3 and x equals 3. If I want to be pedantic, right, that means that the points negative 3 comma 0 and 3 comma 0 show up on my graph. So my intercepts are done. Now I need to find the vertex. Well, to find the vertex, using my relationship above, if I average negative 3 and 3, that should give me its x-coordinate. So for my vertex, its x-coordinate h should be the average of negative 3 and 3. Add them up and divide by 2. Well, negative 3 plus 3 is 0. 0 divided by 2 is 0. So the x value is 0. And if I think about it on a number line, that makes sense. Halfway between negative 3 and 3 would be 0. So when I plug in 0, that should give me the y value of my parabola. Cool. Or not parabola, but of my vertex. So here, x is going to be 0. So I've got 0 squared minus 9. 0 squared is 0. And 0 minus 9 is negative 9. What this, of course, tells me is that x equals 0, y equals negative 9. Here is the value of my vertex. Nice. Let's try it again with this guy. Y equals 2x squared minus 12x plus 16. Go ahead, find me your x-intercepts by making y equal to 0. Use those intercepts to find me a vertex. Go. Okay. Here, for my x-intercepts, again, being really explicit, I need to plug in 0 for y. So I'm going to take my equation here. I'm going to make y equal to 0. And then using the 0 property, if I can factor the other side, I can find my intercepts. So starting by factoring here, look at all these numbers, 2, negative 12, and 16. All of them are multiples of 2. When I factor out a 2, that leaves me with x squared here in my first term, negative 6x in the middle, and plus 8 at the back. Now, inside of my parentheses, notice I've got a quadratic trinomial. So let me set up my two parentheses. I need two numbers at the front to multiply to x squared. That's got to be x times x. At the back, because my leading coefficient is invisible 1, I need two numbers that multiply to get positive 8 and add to get negative 6. Well, that should be negative 2 and negative 4. From here, using the 0 property, I can now split up to find my values of x. So by the 0 property, either 2 is equal to 0, which doesn't make sense, so I can ignore that. X minus 2 could be equal to 0, or x minus 4 could be equal to 0. If x minus 2 is equal to 0, adding 2 to both sides, here x is going to be equal to 2. Adding 4 to both sides in my equation on the right, here x is equal to 4. This tells me that my x-intercepts appear at the points 2, 0, and 4, 0. Nice! Now for my vertex. Remember to find the x value of the vertex, which we often say is h. I need to find the average of the x-coordinates of my intercepts. Well, between 2 and 4 is 3, so I can do that logically. Let's also show it algebraically to confirm. So this is going to be 2 plus 4 divided by 2. 2 plus 4 is 6, and 6 divided by 2 is indeed 3. So here, the x value of my vertex is going to be 3. Let's find the y value by doing some substitution. So y is going to be equal to 2 times 3 squared minus 12 times 3 plus 16. All I got to do now is simplify. So 2 times 3 squared would be 2 times 9. 12 times 3 is 36, and then I've got plus 16 at the back. 2 times 9 is 18. Negative 36 plus 16, I might as well do that now. That's negative 20. And then 18 minus 20 is negative 2. So what this, of course, tells me is that my vertex should appear at the point 3, negative 2.